Let's take a look at another triangle problem. In this case, we want to know, what is the blue charge going to do? If I simply put it here and staple the two red charges down so they don't go anywhere, and let the blue charge go, what will it do? We can find the net force on the blue charge and use that to find the acceleration, or we can find the electric field at this point and get the same information, not just for this blue charge, but any other negative charge we happen to find. Our modus operandi is clear. First and foremost, deal with the directions. Draw that star. Make sure you know which way your charge will move. Which way is the left charge going to make this top charge move? Draw it in. Which way is the right charge going to make the top charge move? Draw it in. Once you've dealt with the directions, then we can deal with the numbers. No negatives. Negative is a direction, and direction has been taken care of already. This charge is attracted this way, this charge is attracted that way. Then we can add them up and find the total. For this problem, let's find the electric field up here at the top charge and use that to determine in which direction the top charge will move. As part of our big answering the question, what will it do if we let it go? In your mind, we've got the two red charges stapled down. Put the blue one down and let it go. Which way is it going to move? You sure? You positive? All right, let's find out. There are two ways we can approach the problem. One of them is number crunching, just like Coulomb's law that we did before. Find our angles. There's one, there's the other. This is an equilateral triangle, then this is 60, and this is 60, and this is 60, and that means half of it, right down the middle, is 30 on this side, 30 on that side. Down is 270 degrees. This is 270 plus 30. This is 270 minus 30. Do we need to do that? Yes, because we need to measure all of our angles from the x-axis. 240 and 300 rather than positive 30 and negative 30. Why? Because positive 30 is over here and negative 30 is over here. Now, we got 50 centimeters from here to here. Whoa, centimeters, we're going to have to convert that to meters. All right, convert that to meters. Let's take a look at the electric field up here where the blue charge is, coming from the red charge on the right. Looks just like Coulomb's law, only the blue charge is now taken out of the equation. It could be another blue charge, so we just have to look at the 10 microcoulombs. Not so bad, huh? Crunch it into your calculator, find the number yourself, write it down, press play, check your work. There you go. Got an enormous number of newtons per coulomb. Why? Because a coulomb is ridiculously large. Now, should be the same electric field on the right. Let's take a look at direction. We've got 3.6 times 10 to the 5th newtons per coulomb, or whatever. X component, Y component. Type that in. Press enter. Got it. Saved it. All right. Should be much the same thing on the right. Let's try it on the right. Same number, same charge, different direction. Cosine theta, sine theta, find those components, type it in, press enter. What do we get? Hey, not quite the same thing. Close. Add them up. What do you get? 1.8, negative 1.8, 0. Negative 3.1, negative 3.1, negative 6.2 times 10 to the 5th newtons per coulomb. We can use that to find the net force, to find the acceleration. We can also use it to find a massive shortcut. We don't necessarily need to crunch all these numbers and all those components to find out what the blue charge is going to do. Which way did you say the blue charge was going to move? Did you say down? You're right. And you were right even before you crunched the numbers. Let's work with it. Look, we had a force from the left and a force from the right. They were perfectly symmetrical. 30 degrees on this side, 30 degrees on that side. Same charge, same distance from center to center, same angle, one on the left, one on the right. That means they're going to have the same y components and the same x components, one to the left, one to the right. Same on the left plus same on the right is going to give us 0. Now, there are two y components. This one goes down. This one all goes down, but they're identical. Add them up. You're going to get 1 down plus 1 down equals 2 down. We can see with our eyes ahead of time that the x components are simply going to cancel out. How? by symmetry. They're the exact same thing on the left and on the right. We can see with a little bit more thought that the y components are going to double. Why? Because they're exact same thing. One down, one down. Last time I checked, that was 2 down. 2 what? Our formula. KQ over R squared for electric field, or KQQ over R squared for Coulomb's law. The y component is going to be the sine component. We can save ourselves a lot of number crunching. We can do half as much typing if we look at this problem by symmetry. Now, we have a new to-do list for highly symmetrical problems that we can recognize by equal charges, equal spacing, and equal everything we look. First step, cancel out the horizontal forces. The left one has a horizontal force, pulling it left. The right one has a horizontal force, pulling it right. Both of those are going to go. The vertical forces, one of them is pulling down, the other one is also pulling down. They are going to add. And overwhelmingly, the net force will be downward. And the whole point of answering this question was to see where is this blue charge going to move when we let it go. That blue charge is unquestionably going to move down. Then what? What happens to the net force after it's moved a little bit further this way? I submit to you that the net force decreases as you go down. Why? The electric field decreases as you go down. We've got our formula. It's 2 y components, whatsoever they may be, some number times sine theta. Sine theta decreases as you go down. If you insist that I prove it like some poor college freshman physics major trying very much to prove their worth to some professor whose lab they want to work in, fine. R squared is x squared plus y squared, Pythagorean theorem, and sine theta is opposite over hypotenuse, that's y over x squared plus y squared. Look, electric field, and therefore the net force, is directly proportional to y. Y goes down, electric field goes down too. If you point out that there's also a y in the denominator, I applaud you for noticing. Graph this function on your calculator as a function of y and some constants that you can set. Hey, graph it on Desmos. Set the constants to be something sensible. You will see that although this function does not decrease linearly, it makes a very good linear approximation when you're very close to the axes. One way or another, the net force is going to decrease as you go down, because the y component is going to decrease as you go down. Now, when you get to the middle, right here, what's the net force? That's a question that you could have answered yesterday or the day before. That's a question that probably a freshman could answer if we explained the problem to them patiently enough. There's no question, but the net force in the middle is 0. It's our old equilibrium problem. Everything's perfectly balanced. Now, when the net force is 0, what's the particle going to do? Careful. Press pause, think about it, and then press play again. When the net force is 0, what is that charge going to do? You sure? That's right. It's going to keep doing what it was already doing. We call this inertia. We call this conservation of momentum. When the net force is 0, the 1 microcoulomb charge does not stop. It keeps going. And it keeps going in the same direction and the same speed that it was going before, because conservation of momentum. There's no outside force interfering. Whoa, 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 whoa. What is that going to mean? If the net force decreases as you go down, it means you're still accelerating. You're still picking up speed, but you're picking up less speed than you expected to until you get to the middle. There's no net force, and you are not picking up any speed at all. You keep moving at a constant speed. Then your inertia keeps you moving at that speed until an outside force interferes, and that outside force is going to slow you down as it pulls you right back up. You pick up speed on the way up and end up crossing at a constant speed until you're up on this side when the force starts to slow you down as you pull it down again by symmetry. You're going to spend an identical displacement slowing down. You'll be back up here again right where you started, and up, down you'll go again. This is simple harmonic motion. we can set up a differential equation for the net force coming down when you're up and the net force coming up when you're down. That's a restoring force, and restoring forces will make things vibrate up and down in a sinusoidal pattern, back and forth and back and forth, assuming friction doesn't run it down.